What if I told you that the universe played by entirely different rules in its very first moments? Rules so strange they seem ripped straight from science fiction. Picture this: an entire cosmos stretching itself apart faster than light itself could travel, defying the very laws that govern reality as we know it. This isn't some wild fantasy, it's cosmic inflation, one of the most mind-bending ideas in modern physics, and it might just hold the key to understanding how everything we see around us came to be. Think about the universe today, a vast, slowly expanding tapestry of galaxies, stars, and planets. Now rewind time to the very beginning, less than a trillionth of a second after the Big Bang. Here, in this unimaginably tiny sliver of existence, something extraordinary happened. Space didn't just expand, it exploded outward at a rate so extreme it would make even the speed of light seem sluggish. How is that possible? And more importantly, why would the universe behave in such a bizarre way? These are the questions that keep physicists up at night, because cosmic inflation doesn't just challenge our understanding, it turns it upside down. Yet here's the wildest part. This theory, as counterintuitive as it sounds, might be the best explanation we have for the universe we see today. It solves puzzles that have baffled scientists for decades, like why the cosmos looks so uniform in every direction or how galaxies could form so quickly after the Big Bang. But with every answer comes new mysteries. What triggered this runaway expansion? What strange physics governed those first moments? And could there be other universes out there born from the same explosive process? Buckle up, because we're about to dive into one of the most thrilling frontiers of science, where logic takes a backseat, and the universe reveals just how little we truly understand. The story of cosmic inflation begins not with a sudden flash of inspiration, but with a stubborn problem that refused to go away. In the late 1970s, physicist Allen was wrestling with one of cosmology's biggest headaches. Why does the universe look so eerily similar in every direction? No matter where we point our telescopes, the cosmic microwave background, the faint afterglow of the Big Bang, shows nearly identical temperatures across billions of light years. That shouldn't make sense. Without some extraordinary mechanism, distant regions of space would never have had time to reach equilibrium, leaving the cosmos patchy and uneven. But reality tells a different story. His breakthrough came when he realized the early universe might have a period of hypercharged expansion, smoothing out wrinkles in spacetime like a balloon inflating to cosmic proportions. Imagine two dots on the surface of a deflated balloon. Before inflation, they could exchange heat and particles easily. But if that balloon suddenly expanded a trillion times in a fraction of a second, those dots would be flung impossibly far apart. Yet they'd still carry that original, uniform temperature. This wasn't just a tweak to the Big Bang theory. It was a radical rewrite of cosmic history. But here, where things get truly bizarre. According to relativity, nothing can move faster than light through space. But space itself has no such speed limit. Think of it like a cosmic treadmill. If space stretches beneath your feet, you're not breaking any rules by being carried along faster than light could travel in a static universe. Inflation takes this loophole and runs wild with it, suggesting the early cosmos expanded so rapidly that regions now separated by billions of light years were once cozy neighbors. Yet for all its explanatory power, inflation remains deeply controversial. Some physicists argue it's too flexible, a theory that can explain almost any observation by tweaking its parameters. Others point out we've never directly detected the primordial gravitational waves inflation should have left behind. And then there's the unsettling implication that our universe might just be one bubble in an endless froth of inflating space-time, each with its own laws of physics. What started as a solution to a cosmic puzzle has blossomed into one of science's most profound and perplexing frontiers: cosmic speed limit. The idea that nothing can outpace light seems like an ironclad rule. Yet cosmic inflation flips this notion on its head, not by breaking relativity, but by exploiting a subtle loophole hidden in its fine print. The trick lies in the difference between moving through space and the expansion of space itself. Imagine you're standing on a stretchy fabric. If you try to run across it, there's only so fast you can go. But what if someone suddenly pulled the fabric taut, stretching it beneath your feet? You wouldn't be moving faster, the ground itself would be carrying you away. That's exactly how inflation works. Space isn't pushing matter faster than light, it's the arena of reality itself that's swelling at an unimaginable rate, dragging galaxies, energy, and even time along for the ride. This distinction resolves the paradox, but it also opens a door to even stranger possibilities. If space can stretch faster than light, could there be regions of the universe forever hidden from our view, their light never able to reach us across the expanding gulf? Astronomers call this the observable universe, the portion we can see. But inflation suggests the true cosmos might be infinitely larger, with countless galaxies receding beyond our cosmic horizon. It's like being adrift in an ocean where distant shores vanish over the curve of the horizon, not because they've moved, but because the sea between you is stretching into an unfathomable expanse. Yet this elegant solution raises new questions. What force could drive space to inflate so violently? The leading suspect is a mysterious field called a sort of cosmic fuel that powered the universe's exponential growth. Picture a ball rolling down a hill gathering speed, except in this case, the hill is an energy landscape unlike anything in today's universe, and the ball's descent triggers a runaway expansion that reshapes reality itself. When the finally settled into its lowest energy state, the energy it released flooded the cosmos with the particles and radiation that would later coalesce into stars and planets. But here's the catch. We've never directly detected them. It's a ghost in the equations, a theoretical construct that beautifully explains what we see yet remains just out of reach. The implications ripple even further. If space can stretch faster than light once, could it happen again? Some theories suggest our universe might be caught in an endless cycle of inflation, with new bubbles of reality constantly budding off from an eternally expanding background. It's a dizzying thought that beyond the edges of our cosmic bubble, other universes might be blossoming with entirely different laws of physics, their existence forever separated from ours by the unbridgeable speed of inflation. This is where cosmology collides with philosophy. Inflation doesn't just challenge our understanding of physics, it forces us to grapple with the very nature of reality. Are we living in a finely tuned universe, or is ours just one accidental outcome in a multiverse of infinite possibilities? The speed limit paradox isn't just a quirk of math, it's a window into a deeper mystery, one that reminds us how much of the cosmos still defies our grasp. And as telescopes peer deeper into the cosmic microwave background and gravitational wave detectors strain to hear whispers from the Big Bang, we inch closer to answers that might rewrite not just the story of our universe, but our place within it. At the quantum level, reality is never perfectly still. Even in the vacuum of empty space, particles flicker in and out of existence in a restless dance of energy. These fleeting quantum fluctuations might seem insignificant, but during inflation, they were stretched to cosmic proportions, becoming the hidden seeds that shape the entire universe. Picture a calm pond suddenly expanding to the size of an ocean. Tiny ripples on its surface would grow into vast, rolling waves. In the same way, microscopic quantum jitters were by inflation's explosive expansion, imprinting faint wrinkles onto the fabric of spacetime itself. These wrinkles became the scaffolding for everything we know. Denser regions, where fluctuations piled up just slightly more, pulled in extra matter through gravity over billions of years, eventually collapsing into galaxies and stars. Meanwhile, emptier patches stretched into the cosmic voids between them. It's a staggering thought. Every galaxy, every planet, every atom in your body might trace back to random quantum tremors frozen into the universe during its first fraction of a second. Yet this raises a profound question. How does chaos create such breathtaking order? Quantum fluctuations are inherently random, Yet the universe we see displays an eerie large-scale uniformity alongside intricate structures. Inflation solves this paradox by acting like a cosmic amplifier. Imagine rolling dice trillions of times. Over enough throws, even randomness starts to form patterns. Inflation took quantum noise and stretched it across the cosmos, smoothing it into subtle density variations that gravity later sculpted into the web of galaxies we observe today. The evidence for this is etched into the cosmic microwave background, the universe's baby picture. Satellite maps reveal temperature variations, hotter spots where matter was denser, cooler spots where it was thinner, matching predictions from quantum fluctuations with stunning precision. It's as if we're seeing the fingerprints of inflation itself, a snapshot of the universe's quantum origins writ large across the sky. But the mystery doesn't end there. If inflation truly stretched quantum ripples into cosmic structures, what does that say about the nature of reality itself? Some theorists suggest we might be living in a universe where chance plays a far deeper role than we imagined, where the fundamental properties of space, time, and even the laws of physics could be the result of quantum accidents frozen into existence during those first moments. It's a humbling reminder that the universe's grand design might owe as much to randomness as it does to the elegant laws we've worked so hard to uncover. If inflation truly happened the way physicists suspect, then our universe might be just one tiny bubble in an endless cosmic foam. Picture a pot of boiling water, not with bubbles of steam, but with entire universes, each nucleating in the seething energy of an eternally inflating spacetime. This is the multiverse hypothesis, where inflation doesn't stop everywhere at once. Some regions slow down and cool off, forming stable pockets like ours, while others continue expanding wildly, birthing new universes in an infinite cascade. What's staggering about this idea isn't just the scale, it's the implications. Each of these bubble universes could have entirely different physical constants. The strength of gravity, the mass of electrons, even the number of dimensions might shift from one bubble to the next. In some, matter might never clump into galaxies. In others, stars could burn out in an instant. Our universe, with its delicate balance allowing for planets and life, might be a rare oasis in a desert of inhospitable realities. Critics argue this sounds less like science and more like metaphysics. After all, if other universes are forever beyond our observation, how could we ever test their existence? But supporters counter that the multiverse isn't just wild speculation, it's a natural consequence of inflation's math. When quantum fluctuations drive the inflationary field, some regions inevitably drop out of expansion sooner than others, like patches of dew forming randomly on a cold window. The real controversy is whether the multiverse could exist, but whether it's a meaningful scientific idea if we can't falsify it. Yet clues might still lurk in our own cosmic backyard. If our universe collided with another bubble long ago, the shockwave could have left scars in the cosmic microwave background, subtle temperature anomalies that future telescopes might detect. Even stranger, some theories suggest dark energy, the mysterious force accelerating our universe's expansion, could be a remnant of the field, a faint echo of the process that birthed our bubble. The multiverse forces us to confront humbling questions. Are the laws of physics fundamental truths, or just local bylaws in our tiny corner of existence? If infinite variations exist, does that make our universe less special, or more remarkable for having allowed us to ponder it at all? Inflation began as a way to explain the universe we see. But in doing so, it may have opened a door to realities beyond our wildest imagination. Whether those doors lead to deeper understanding or endless speculation is a debate that will shape physics for decades to come. One of the most puzzling features of our universe is how eerily uniform it appears no matter where we look. The cosmic microwave background, that ancient afterglow from the Big Bang, shows nearly identical temperatures in opposite directions. even though those regions are separated by tens of billions of light years. Here's the catch: without some extraordinary mechanism, those distant patches of space should never have had time to reach thermal equilibrium. Light simply couldn't have traveled far enough to even things out. It's like walking into two different kitchens on opposite sides of the planet and finding pots of water boiling at exactly the same temperature, down to a fraction of a degree. How could that happen without some hidden connection? This cosmic conundrum is called the horizon problem, and it's one of the strongest clues that our universe's infancy was far stranger than we once imagined. Enter cosmic inflation, the idea that the entire observable universe was once crammed into a space smaller than an atom, where everything could easily mix and match temperatures before being violently stretched apart. Think of it like a drop of dye in a glass of water. If you gently stir it, the color spreads evenly. But if you suddenly expanded that glass to the size of a swimming pool, the dye would remain uniformly distributed, even though its molecules never had to travel the new, enormous distance. Inflation works the same way, taking a tiny, homogeneous speck of space and blowing it up so rapidly that uniformity gets locked in before expansion pulls regions beyond each other's horizons. Yet for all its elegance, this solution leaves some scientists uneasy. Could inflation be a bit too powerful, a theoretical Swiss Army knife that explains away problems a little too neatly? After all, if any initial irregularities were erased by runaway expansion, how do we test what the pre-inflation universe was really like? It's like smoothing out a crumpled sheet of paper so thoroughly that you can no longer tell what the original creases looked like. Some researchers argue that alternative theories, like variable speed of light models or bouncing cosmologies, might offer competing explanations without invoking such extreme physics. But none have matched inflation's ability to account for both the universe's smoothness and the subtle density variations that seeded galaxies. The debate hinges on a deeper question. Are we seeing a genuine feature of nature, or have we crafted a theory so flexible it can't be disproven? Inflation's parameters can be tweaked to produce wildly different scenarios, some with brief, gentle expansion, others with violent, prolonged stretching. Without definitive observational tests, like detecting primordial gravitational waves from inflation's aftermath, the theory walks a fine line between breakthrough and just so story. What makes the horizon problem so fascinating isn't just the answer inflation provides. It's the reminder that the universe's greatest mysteries often lie in the questions we're only beginning to ask. Take a ruler and try drawing a triangle on the surface of a balloon. As you inflate it, something strange happens. The angles that once added up to 180 degrees start to warp, bending with the curve of the expanding rubber. Now imagine doing the same experiment across the entire universe. Here's the shocker. No matter how precisely we measure, space behaves like a perfectly flat sheet, with triangles obeying the rules of classic geometry as if they were drawn on a tabletop. This cosmic flatness isn't just a curiosity. It's a screaming clue that the universe is balanced on a knife's edge, caught in an exact equilibrium between the outward pull of expansion and the inward tug of gravity. Why does this matter? Think of it like balancing a pencil on its tip. Left to its own devices, it should topple instantly. Yet our universe has somehow maintained this precarious balance for billions of years. Without some extraordinary mechanism fine-tuning the numbers, even a tiny deviation early on would have sent the cosmos spiraling into runaway collapse or chaotic expansion. So how did we end up with a universe that's so perfectly, inexplicably flat? Inflation offers an elegant solution. Picture a marble rolling down a steep hill. The steeper the slope, the faster it accelerates. Now imagine that hill represents the energy density of the early universe. Inflation's explosive expansion acted like a cosmic iron, stretching space so dramatically that any initial curvature became negligible, just as blowing up a balloon smooths out its wrinkles. What started as a slightly curved surface, when stretched to cosmic proportions, appears flat to any observer within it. like an ant on a football field perceiving the Earth as perfectly flat. But this raises a deeper question. Is flatness just a side effect of inflation, or does it point to something more profound? Some theorists suggest it might be evidence of a multiverse, where countless other universes with different curvatures exist beyond our horizon. In this view, we find ourselves in a flat universe not by chance, but because only such a finely tuned cosmos could support galaxies, stars, and ultimately life. It's a modern twist on the anthropic principle, the idea that the universe's properties are conditioned by the necessity of observers existing to measure them. Others argue that flatness might hint at undiscovered symmetries or conservation laws woven into the fabric of reality. Just as equations revealed that energy and spacetime are fundamentally linked, future breakthroughs could uncover a hidden principle that locks the universe into geometric perfection. Or perhaps flatness is a mirage, a temporary state in a cycle of cosmic contraction and rebirth, like a pendulum pausing at the bottom of its swing before reversing direction. The mystery cuts to the heart of cosmology's greatest challenge, distinguishing between features that are inevitable outcomes of physical laws and those that are mere accidents of our particular cosmic neighborhood. Every time we measure the universe's geometry with greater precision, whether through the cosmic microwave background or the large-scale distribution of galaxies, we're not just collecting data. We're interrogating reality itself, searching for whispers of the forces that set the stage for everything we know. And in that search, flatness isn't just an answer. It's a doorway to questions we're only beginning to frame. The universe has a curious habit of balancing its books. Every north magnetic pole comes paired with a south, every positive charge with a negative. But in the early 1930s, physicists made a startling prediction. There should exist particles carrying just a single magnetic charge, isolated north or south poles wandering free like electrical charges do. These hypothetical relics, dubbed magnetic monopoles, would be cosmic oddballs, massive, stable, and packing a punch strong enough to disrupt atoms with their sheer magnetic might. If they existed, we'd have found them by now. Yet after decades of searching, from deep underground detectors to scans of ancient meteorites, not a single confirmed monopole has turned up. This absence isn't just a minor puzzle, it's a glaring inconsistency in our understanding of the early universe. Grand unified theories, which attempt to stitch together the fundamental forces, suggest monopoles should have been produced in staggering numbers during the extreme energies of the Big Bang. So where did they all go? Inflation steps in with a bold answer. They weren't destroyed, they were diluted to near invisibility. Picture a drop of ink in a bathtub versus that same drop in an ocean. Inflation's exponential stretching would have scattered monopoles so thinly across space that finding one today would be like searching for a single grain of sand in a galaxy-sized desert. But not everyone finds this explanation satisfying. Critics argue that invoking inflation to erase monopoles feels suspiciously convenient, like rewriting a mystery novel after realizing the original plot had too many loose ends. If a theory can effortlessly sweep away its own contradictions, does that make it robust or untestable? Some physicists propose alternatives. Perhaps monopoles were never created in the first place because grand unified theories need revision, or maybe they decayed into other particles over cosmic time. Others suggest they're hiding in plain sight, masquerading as dark matter or lurking in regions of space we've yet to explore. The debate cuts to the heart of how science grapples with missing evidence. Is inflation's monopole solution a stroke of genius, patching a hole in our cosmic narrative? Or is it a clever workaround that lets theorists off the hook? The answer might lie in future experiments. If we ever do detect a monopole, its properties could reveal whether inflation truly stretched them beyond our reach, or if the universe has been playing a different game all along. Until then, their absence remains both a triumph for inflation's explanatory power and a nagging reminder that the early cosmos still holds secrets we've only begun to unravel. While inflation has become the leading framework for explaining the universe's early moments, it's far from the only game in town. Some cosmologists argue that its very flexibility, the way it can be tweaked to explain almost any observation, is a weakness, not a strength. Enter the bouncing universe hypothesis, a radical alternative that swaps the Big Bang for a cosmic rebound. Instead of a singular, explosive beginning, this theory suggests our universe emerged from the collapse of a previous one, like a phoenix rising from its own ashes. Picture a rubber ball hitting the ground. At the moment of maximum compression, all that energy has to go somewhere. In this scenario, the extreme densities of the bounce could have smoothed out wrinkles in space-time and set the stage for expansion. No inflationary period required. But the bouncing model comes with its own challenges. For one, it requires physics beyond relativity to explain how a collapsing universe could rebound without violating energy conservation. Some versions invoke quantum gravity effects, where the fuzzy uncertainty of the quantum world prevents total collapse, acting like an invisible trampoline at the smallest scales. Others propose extra dimensions or exotic matter to fuel the bounce. While elegant in theory, these ideas lack the observational support inflation enjoys. No telltale signatures in the cosmic microwave background have yet confirmed a bounce occurred. Then there's emergent gravity, an even more unconventional approach. What if gravity isn't a fundamental force at all, but an illusion, a side effect of deeper, hidden processes in the fabric of space-time? Think of how temperature emerges from the chaotic motion of atoms. You can't point to a single molecule and say that's heat, yet the collective behavior creates something entirely new. Emergent gravity frameworks suggest that the early universe's expansion might not need a field or exotic bounce, just a reorganization of how space itself stores information. The appeal of these alternatives lies in their ability to sidestep inflation's thorniest issues, like the multiverses or the field's elusive nature, but they face their own hurdles. Without a smoking gun prediction like inflation's gravitational waves, it's hard to pit them against each other experimentally. And while inflation's parameters might feel adjustable, emergent theories often rely on equally speculative mathematics. This isn't just academic turf warfare, it's a healthy tension that drives science forward. Every time inflation's critics poke at its soft spots, supporters refine the theory to address them. When alternatives propose bold new mechanisms, they force everyone to long-held assumptions. The best outcome might not be a winner-takes-all victory, but a synthesis. Perhaps some hybrid model blending inflation, stretching with quantum bounces or emergent effects will ultimately explain our universe's first moments. Until then, the debate itself is a reminder of how much we still have to learn about the cosmos's grand opening act. Dark energy is the universe's greatest unsolved puzzle, a mysterious force pushing galaxies apart faster and faster, as if space itself has a hidden accelerator pedal. But here's the eerie part. This acceleration mirrors, in slow motion, the universe's explosive growth during cosmic inflation. Both episodes involve space stretching at a mind-bending pace, separated by billions of years. Is this just a cosmic coincidence, or could dark energy be inflation's distant cousin, a faint echo of the same process that jump-started everything? The similarities are striking. Inflation was driven by a hypothetical energy field, though that flooded the early universe with repulsive gravity, causing space to expand exponentially. Today, dark energy behaves like a weaker version of that same repulsion, gently but relentlessly stretching the cosmos. Some theorists suggest dark energy might even be the field's leftover energy, diluted over eons but never entirely vanishing. Picture a campfire that's burned down to embers, still faintly glowing, still capable of warming your hands. If this connection holds, we're witnessing the final whispers of the same force that birthed the universe. But not everyone's convinced. Skeptics point out key differences. Inflation was unimaginably brief and intense, while dark energy's influence is subtle and persistent. It's like comparing a supernova to a candle. Both emit light, but their scales and mechanisms couldn't be more different. Alternative explanations range from dark energy being a property of empty space itself, infamous cosmological constant, to evidence of extra dimensions leaking gravity into our universe. The most radical idea, dark energy isn't constant at all, but a slowly evolving field that might one day shut off, or worse, rip the cosmos apart in a Big Rip scenario. The stakes couldn't be higher. If dark energy and inflation share a common origin, it would mean the universe's birth and death are bookended by the same physics, a poetic symmetry hidden in the equations. But if they're unrelated, we're left with two colossal mysteries instead of one. Future telescopes, like the observatory, could tilt the balance by measuring dark energy's behavior with unprecedented precision. Does its strength change over time? Does it interact with matter in ways we haven't yet detected? Each clue brings us closer to understanding whether we're living in a universe with a hidden, or one where history's greatest expansion events are just cosmic. Proving cosmic inflation happened isn't like catching a suspect on camera. It's more like uncovering fingerprints at a crime scene billions of years cold. The evidence lies in whispers from the early universe, subtle signals buried in the static of cosmic background radiation and the faint ripples of spacetime itself. One of the most promising clues, primordial gravitational waves, undulations in the fabric of reality triggered by inflation's violent expansion. Picture throwing a pebble into a pond. The ripples spread outward, fading but never entirely disappearing. Inflation should have sent similar tremors through spacetime, their echoes lingering as a faint, telltale swirl in the polarization of the cosmic microwave background. Detecting these waves would be like finding the universe's birth certificate, but the hunt is fiendishly difficult. Experiments like Bicep and the satellite have scoured the skies, teasing apart inflationary signals from competing noise like interstellar dust. In 2014, a team thought they'd struck gold with a detection, only to later realize galactic interference the data. It's a reminder that inflation's smoking gun remains just out of reach, hidden behind cosmic static. Yet gravitational waves aren't the only test. The cosmic microwave background itself is a treasure trove of inflationary clues. Inflation predicts specific patterns in temperature fluctuations, tiny hot and cold spots that should follow a statistical signature unlike any random process. So far, the data aligns beautifully, like a key sliding into a lock. But here's the catch. Alternative theories can sometimes mimic these patterns, leaving room for debate. It's the scientific equivalent of distinguishing between identical twins by their fingerprints, possible, but requiring impossibly precise measurements. Then there's the distribution of galaxies across the universe. Inflation's quantum fluctuations should have left a distinct fingerprint on large-scale structure, like an invisible hand arranging matter into a cosmic web. Surveys mapping millions of galaxies, like the Sloan Digital Sky Survey, reveal a web-like distribution eerily consistent with inflationary predictions. But critics argue this is conclusive. After all, other processes could potentially weave similar patterns over billions of years. The challenge isn't just technical, it's philosophical. How do you test a theory about a one-time event that reshaped reality itself? Inflation's flexibility, while initially a strength, makes it notoriously hard to falsify. Adjust a parameter here, tweak an assumption there, and the theory can accommodate almost any observation. Some scientists argue this makes it less a scientific theory and more a framework, a story that fits the facts too well to disprove. Others counter that absence of disproof isn't proof, and that inflation's explanatory power still outweighs its ambiguities. What's next? Future experiments like the observatory and next-generation gravitational wave detectors aim to push sensitivity to new limits, hunting for signals too faint for current technology. Some theorists even propose wilder tests, like searching for colliding bubble universes in the cosmic background, scars from other inflationary events beyond our own. Whether these efforts confirm inflation or send physicists back to the drawing board, one thing's certain: the quest to understand the universe's first moments is far from over. And that's the beauty of science. It's not about having all the answers, but knowing which questions to ask next. In 2014, the physics world buzzed with excitement when the Bicep 2 team announced they'd glimpsed something extraordinary, a distinctive swirling pattern in the cosmic microwave background that seemed to match predictions for primordial gravitational waves from inflation. This wasn't just another data point. It was potential confirmation of the universe's most dramatic growth spurt, a smoking gun etched into the afterglow of the Big Bang. Media outlets hailed it as a breakthrough, and for a brief moment, it felt like cosmology's biggest mystery might finally be solved. But science has a way of humbling even the most confident claims. When independent researchers scrutinized the data, they realized the signal wasn't purely cosmic. It was muddled by interference from interstellar dust within our own galaxy. Those elegant swirls weren't just echoes of inflation. They were partly the fingerprint of mundane particles floating between the stars. The disappointment was palpable, but the episode wasn't a failure. It was in how science self-corrects. What made the Bicep 2 saga so instructive wasn't the mistake itself, but how the scientific community responded. Instead of digging in their heels, the team collaborated with rival researchers working on the satellite, cross-checking data to separate cosmic signals from galactic noise. The result: a sharper understanding of the challenges involved in hunting inflation's fingerprints. Dust polarization, it turned out, could mimic the very patterns theorists had hoped would prove inflation, a cosmic curveball no one had fully anticipated. This setback forced physicists to confront an uncomfortable truth. The universe doesn't hand us clean answers. Detecting primordial gravitational waves is like trying to hear a whisper in a hurricane. Every signal has to be disentangled from competing noise, not just dust, but the glow of distant galaxies, the ripple of galaxy clusters, even the quirks of our own instruments. The Bicep 2 experience didn't disprove inflation. It revealed just how painstaking the search for evidence would need to be. Yet the pursuit didn't end there. It evolved. New experiments like the observatory and next-generation telescopes are now designed with these lessons in mind, armed with advanced detectors and multi-frequency observations to filter out dust's deceptive signals. Scientists have also expanded the hunt beyond gravitational waves, looking for secondary signatures, subtle distortions in the distribution of galaxies or anomalies in the cosmic microwave, background's temperature variations that might betray inflation's handiwork. The deeper lesson here transcends any single experiment. Science advances not in straight lines, but through a messy, iterative dance of claim and counterclaim, hope and... What Bicep 2 taught us isn't that inflation is unprovable, but that uncovering the universe's deepest secrets demands both boldness and humility, the courage to chase elusive signals, and the wisdom to admit when the data tells a different story. And in that tension between what we expect to find and what the cosmos reveals, lies the thrilling uncertainty that keeps physics alive. String theory's vision of the cosmos reads like something from the most ambitious science fiction. A universe woven from tiny, vibrating strings, humming in higher dimensions we can't perceive. But what if this elegant framework holds the key to unlocking cosmic inflation's deepest secrets? Some theorists suggest that inflation's breakneck expansion might not stem from a lone field, but from the dance of these multidimensional strings. Imagine plucking a guitar string. The note you hear depends on how it vibrates. In string theory's symphony, the universe itself could be the music, with inflation as a sudden, dramatic crescendo triggered by strings shifting into new vibrational states. The connection goes even deeper. String theory requires at least 6 extra spatial dimensions beyond the familiar 3, all curled up into vanishingly small shapes. Inflation might have been the moment when some of those dimensions unfurled, stretching our 3-dimensional space while keeping the others tightly wound. Picture a balloon with intricate wrinkles. When you blow it up, the main surface smooths out, but the tiny creases remain. If true, inflation didn't just shape the universe we see. It locked away entire dimensions in its wake, leaving only faint traces in the fabric of reality. Yet this elegant merger of ideas comes with hefty caveats. String theory itself remains unproven, a dazzling mathematical edifice without experimental confirmation. Critics argue that linking it to inflation risks stacking speculation atop speculation, like using one mystery to solve another. Others counter that the math reveals startling convergences. Certain string theory models naturally produce like fields, while others suggest inflation could be a collision between higher dimensional branes, membrane-like structures floating in a bulk space. It's as if 2 incomplete puzzle pieces, when pressed together, suddenly reveal a clearer image. The stakes couldn't be higher. If string theory and inflation are truly intertwined, we might finally understand why the field existed at all, not as an ad fix, but as an inevitable consequence of deeper physics. But the path to verification is murky. String theory operates at energies trillions of times higher than any particle collider can reach, and its extra dimensions might be forever hidden from view. Some hope that future gravitational wave detectors could catch whispers of stringy vibrations from the early universe, or that subtle anomalies in the cosmic microwave background might betray higher dimensional fingerprints. What's fascinating isn't just the potential answer, but the way these theories force us to rethink reality's foundations. If inflation emerged from strings dancing in hidden dimensions, it would mean our universe's birth wasn't a singular event, but a ripple in something far grander, a cosmic overture played on a multidimensional stage. Whether this vision is profound truth or beautiful mirage remains one of physics' most tantalizing open questions. The moment before inflation remains one of the most perplexing gaps in our cosmic story, like arriving at a play just as the curtain rises, missing the crucial backstage preparations that set everything in motion. If inflation was the universe's grand opening act, what cued the lights? The unsettling truth is that inflation doesn't explain its own origins. It merely describes what happened once the process began. This isn't just a minor oversight, it's a gaping hole in the narrative, leaving scientists to grapple with a dizzying question. How does nothingness spontaneously ignite into a universe? One provocative idea is quantum tunneling, a phenomenon where particles seemingly teleport through barriers they shouldn't be able to cross. In the subatomic world, this happens constantly. Electrons vanish from one orbit and reappear in another without traversing the space between. Apply this to the cosmos, and you get a wild possibility. Our universe might have tunneled into existence from some primordial state of instability. Picture a marble resting in a shallow dip on a hillside. Normally, it would stay put, but quantum weirdness lets it occasionally phase through the slope, rolling downhill and triggering cosmic expansion. The catch: this hillside would exist in a realm beyond space and time, a landscape of pure potential where the rules of physics as we know them don't yet apply. Others propose inflation was sparked by sheer random chance, a quantum fluctuation so colossal it birthed reality itself. In the frothy chaos of the quantum vacuum, particles flicker in and out of existence constantly. Most vanish as quickly as they appear, but what if one fluctuation didn't fade away? What if, against all odds, it ballooned into an entire universe? It's like blowing soap bubbles. Most pop instantly, but occasionally one detaches and grows, becoming something vast and beautiful. The odds are astronomically low, but given infinite time, or perhaps an infinite multiverse, even the impossible might become inevitable. Yet these theories raise thorny philosophical dilemmas. If inflation began with a quantum event, does that mean our universe is fundamentally accidental? Or was there some deeper mechanism, a law of laws that orchestrated the process? Some theorists turn to loop quantum gravity, a framework where spacetime is woven from discrete, indivisible threads. Here, the Big Bang might not have been a true beginning, but a rebound from a previous universe's collapse. Imagine a cosmic heartbeat. Contraction, bounce, expansion, no mysterious starting gun required. The challenge isn't just scientific, it's almost mythological. Every culture has its creation story, and physicists are no different. Inflation's unanswered why forces us to confront the limits of our tools. Without a time machine, can we ever peer behind the curtain of time, that first fraction of a second where even the concept of before loses meaning? Future experiments might offer indirect clues, subtle asymmetries in the cosmic microwave background or signatures of pre-inflationary relics. But for now, the trigger remains hidden, a reminder that the universe guards its deepest secrets fiercely, and perhaps that's fitting. After all, what's more human than staring into the void and daring to ask, how did this all begin if inflation isn't just a one-time event but a never-ending process? The implications are staggering. Our universe could be a single bubble in an infinite foam of expanding realities. Picture a pot of water set to boil eternally, with new bubbles constantly forming and drifting apart. In this scenario, inflation doesn't stop everywhere at once. Some regions settle into stable universes like ours, while others keep stretching exponentially, birthing new cosmic pockets with every passing moment. This is eternal inflation, a theory so vast it redefines our place in existence. What makes this idea so provocative isn't just the scale, it's the sheer unpredictability of the outcomes. Each bubble universe could emerge with its own unique laws of physics, like rooms in a cosmic hotel where the rules change behind every door. Some might have gravity so weak it can't hold stars together, others with forces so strong atoms crush instantly. Ours, with its delicate balance allowing for galaxies and life, might be a rare fluke in an ocean of inhospitable realities. The unsettling question isn't just whether other universes exist. It's whether we're living in the only one that could produce beings capable of asking the question. Testing such a grand vision might seem impossible, but physicists have a few tricks up their sleeves. If our bubble universe collided with another during inflation, the shockwave could have left scars in the cosmic microwave background, subtle temperature variations shaped like concentric rings. Telescopes scouring the sky for these anomalies are like detectives searching for fingerprints at a crime scene spanning the cosmos. Another clue might lurk in the behavior of dark energy. If it's not perfectly constant but varies slightly over time, it could hint that our universe's expansion is still influenced by the field's fading echo. Yet eternal inflation also forces us to confront the limits of science. If other universes are forever beyond our cosmic horizon, forever receding faster than light can bridge the gap, can we ever truly claim they're real? Some argue this veers into metaphysics, but supporters counter that the math doesn't lie. Eternal inflation emerges naturally from the equations, whether we like it or not. The debate isn't just about physics, it's about what we consider knowable. Are we content with a theory that explains everything but can't be fully tested? Or do we hold out for something more tangible? The most profound consequence might be philosophical. If eternal inflation is true, our universe loses its special status, becoming a statistical inevitability in an infinite multiverse. There's no guiding hand, no fine-tuning, just endless rolls of the dice. Yet oddly, this doesn't diminish the wonder. Instead, it amplifies it. Every galaxy, every atom, every moment of consciousness becomes a rare spark in the cosmic dark, a fleeting pattern in the infinite whirl of possibilities. Whether eternal inflation is the final word or just another step toward deeper truths, it reminds us that the universe's mysteries are far stranger and far more beautiful than we ever imagined. Imagine flipping a coin in a universe where every possible outcome happens somewhere. Heads here, tails there, and even bizarre possibilities where the coin lands on its edge or turns into a flock of birds midair. In an infinite multiverse spawned by eternal inflation, this isn't just a thought experiment, it's a statistical crisis. If every conceivable event occurs in some pocket of reality, how do we distinguish the probable from the inevitable? This is the measure problem, a paradox so deep it shakes the foundations of how we do science. At its core, the issue is about counting. Normally, probabilities are straightforward. Roll a die and each face has a 1 in 6 chance. But in a multiverse where infinite versions of you are rolling infinite dice, every outcome, from snake eyes to a tower of balanced dice, happens an infinite number of times. Infinity divided by infinity is mathematically undefined, leaving us with no clear way to say which results are likely. It's like trying to weigh a mountain by counting all its atoms. When everything is endless, the numbers lose meaning. Physicists have proposed workarounds, but each comes with its own headaches. One approach is to impose a cutoff, counting only the outcomes in a finite slice of the multiverse. Think of it like sampling a spoonful of soup to judge the whole pot. But who decides which spoonful is representative? Another idea is to weight probabilities based on how often different bubble universes form. Some might be rare, like cosmic jackpots, while others are as common as grains of sand. Yet without a way to observe these bubbles, the math feels like guesswork dressed in equations. The stakes couldn't be higher. If we can't define probabilities in a multiverse, does the concept of scientific prediction collapse? After all, science thrives on falsifiability, the ability to say some outcomes are more plausible than others. If everything happens somewhere, even the wildest theories become. String theory's landscape, for instance, suggests there are 10 to the 500 possible vacuum states, each corresponding to a universe with different physical laws. Without a measure to compare them, the theory risks explaining nothing by claiming everything. Critics argue this exposes a flaw in multiverse thinking, that it's less a scientific theory and more a philosophical stance. Supporters counter that the measure problem isn't unique to cosmology. Even in quantum mechanics, the many worlds interpretation grapples with similar issues when branching realities multiply endlessly. The real challenge might be accepting that our intuition, honed in a finite world, simply isn't equipped to navigate infinity. Perhaps the solution lies not in discarding the multiverse, but in redefining what science can ask of it. Instead of seeking absolute probabilities, maybe we focus on relative likelihoods within our observable patch of reality. After all, we don't need to count every star in the cosmos to understand how our sun works. The measure problem doesn't just test our math. It forces us to confront what it means to know something in a universe where the rules might be stranger and far more vast than we ever imagined. The idea of a universe that endlessly dies and rebirths itself carries an almost mythic beauty, a cosmic phoenix rising from its own ashes in an eternal dance of destruction and renewal. Cyclic cosmology dares to ask, what if the Big Bang wasn't a beginning, but just another turn in an infinite loop? In this vision, inflation isn't a one-time spark, but a recurring phase, like the deep breath a universe takes before expanding anew. The appeal is undeniable. Instead of a single, inexplicable origin, we get a rhythm as old as time itself, collapses leading to bounces, bounces birthing new expansions, all woven into an unbroken chain of existence. But poetry alone doesn't make for good science. The real test lies in whether this elegant idea can explain the universe we see. Proponents point to key clues: the eerie flatness of space-time, the uniformity of the cosmic microwave background. Features inflation explains, but that could also emerge from a prior universe's collapse. Imagine kneading dough over and over. Eventually, it becomes smooth and even. Similarly, each cosmic cycle might erase irregularities, leaving the next universe primed for a fresh start. Even the arrow of time, that mysterious flow from past to future, could flip during a bounce, resetting the cosmic clock with each rebirth. Yet cyclic models face daunting challenges. For one, they require physics beyond relativity to prevent the universe from collapsing into a singularity, a point of infinite density where the known laws break down. Some theories invoke quantum gravity effects, where the fuzzy uncertainty of the smallest scales acts like a cushion, softening the bounce. Others propose exotic matter or extra dimensions to redirect collapse into expansion. But these are speculative fixes, lacking the observational support inflation enjoys. No telescope has yet spotted bruises from a previous universe's collapse imprinted on our cosmic background. Then there's entropy, the universe's tendency toward disorder. If each cycle adds to the total chaos, wouldn't future universes grow increasingly ragged over time? Our cosmos seems too finely ordered for countless cycles to have preceded it. Some cyclic models sidestep this by suggesting entropy resets with each bounce, but critics argue this violates thermodynamics' core principles. It's like claiming a shattered vase can reassemble itself perfectly, possible in theory, but wildly improbable without some hidden mechanism. The debate reveals a deeper tension in cosmology. Do we live in a universe with a definitive beginning, or one that's always been recycling itself? Inflation's framework offers testable predictions, like primordial gravitational waves, while cyclic theories often rely on untested physics. But their allure persists because they address a discomforting question: what came before the Big Bang? Inflation leaves that door firmly shut, but cyclic models pry it open, suggesting our universe's birth might be just one chapter in an endless story. Perhaps the most tantalizing possibility is a hybrid approach, where inflation operates within a larger cyclical framework. Imagine a universe rebounding from collapse, then undergoing rapid inflation to smooth its wrinkles before settling into expansion. Such a model could marry the explanatory power of inflation with the grandeur of eternal return. Until we find hard evidence, anomalies in the cosmic microwave background, echoes of pre-Big Bang events, or signs of cyclic physics in particle collisions, the question remains open. What's certain is that both ideas push us to confront the limits of our understanding, reminding us that the cosmos's secrets are stranger than any myth we've ever told. At the heart of inflation's mystery lies an uncomfortable truth. The energies involved were so colossal that gravity itself would have behaved differently, governed by quantum rules we don't yet understand. Picture trying to describe a hurricane using only the physics of gentle breezes. Our current theories, general relativity for gravity and quantum mechanics for the subatomic world, work flawlessly in their own domains, but become hopelessly tangled when pushed to the extremes of the early universe. This isn't just a technical hiccup, it's a chasm in our understanding, one that obscures the very moment when inflation might have been triggered. Quantum gravity's absence leaves us guessing at inflation's ignition. Was it a quantum fluctuation so vast it warped spacetime itself? a collision between higher dimensional brains, as string theory suggests, or something beyond our current imagination. Without a unified theory, these questions hang in the air like unfinished equations on a chalkboard. The irony is stark. Inflation explains so much about the universe's structure, yet we can't fully explain inflation itself. It's like having a detailed map of a continent, but no clue how the landmass formed. Some physicists argue this gap isn't just a nuisance, it's a clue. The fact that inflation's predictions align so well with observations, despite our ignorance of quantum gravity, might mean the theory is robust enough to transcend our incomplete physics. Others see it as a warning sign. If we're missing the rules that governed inflation's onset, could we be overlooking critical side effects? For instance, quantum gravity might have left faint imprints in the cosmic microwave background, twists in polarization or anomalies in temperature fluctuations that current telescopes aren't sensitive enough to detect. The search for quantum gravity's fingerprints has spawned daring experiments. Next-generation gravitational wave detectors, like the proposed Big Bang observer, aim to probe frequencies where spacetime's quantum fuzz might manifest. Other teams scour the cosmic microwave background for subtle statistical quirks, hints that the universe's expansion was seeded by quantum gravitational turbulence. Even particle colliders play a role, recreating, on a puny scale, the energies where gravity and quantum forces might briefly unify. What's fascinating isn't just the scientific challenge, but the philosophical shift it demands. Quantum gravity forces us to reconsider bedrock ideas like causality and time. In the early universe's maelstrom, these concepts might have been fluid, with cause and effect blurring or even reversing. Inflation could have been less a deterministic process and more a quantum roll of the dice, a statistical inevitability in a multiverse where every possible beginning plays out somewhere. The stakes couldn't be higher. If quantum gravity and inflation are entwined, solving one might crack the other. A successful theory wouldn't just fill a textbook gap. It would rewrite the story of cosmic origins, revealing whether our universe's birth was inevitable, accidental, or something stranger still. Until then, we're left with a tantalizing paradox. The best-tested theory of the early universe relies on physics we haven't yet discovered. And that's perhaps the most humbling lesson of all, that the cosmos guards its deepest secrets not in distant galaxies, but in the infinitesimal wrinkles of spacetime itself. Time's relentless march forward feels as natural as breathing. Eggs crack but never, coffee cools but never reheats itself. Memories accumulate but never unravel. This one-way street we call the arrow of time seems baked into reality itself. Yet physics presents us with a paradox. The fundamental laws governing particles don't care about time's direction. Run them backward and they work just fine. So why does the universe? The answer might lie in the aftermath of cosmic inflation, where the seeds of time's arrow were planted in the fiery dawn of existence. Think of entropy like a deck of cards. A new pack comes neatly ordered, kings, queens, and jacks all in place, but shuffle it just once and chaos takes over. The universe works the same way. Inflation's explosive expansion didn't just stretch space, it left the cosmos in a bizarrely pristine low-entropy state, like that untouched deck of cards. This delicate order set the stage for everything that followed, allowing entropy to climb steadily as the universe evolved, creating what we experience as the flow of time. But here's the puzzle. Why was the early universe so orderly to begin with? Inflation smooths out wrinkles in space-time, but it doesn't inherently explain why the starting conditions were so improbably tidy. Some theorists argue that inflation's connection to time's arrow might be even deeper. Quantum fluctuations during those first moments could have imprinted a subtle bias on the universe, like a hidden tilt in the fabric of reality that nudged events toward increasing disorder. Others propose that the arrow of time isn't unique to our universe at all, that in the multiverse, other bubbles might have arrows pointing in different directions. with causality running backward or even in loops. Imagine a room where some clocks tick forward, others backward, and a few spin wildly with no direction at all. Our experience of time might just be a local accident, a quirk of our cosmic neighborhood. Yet skeptics push back. If inflation set time's arrow in motion, why don't we see regions where entropy decreases, even statistically? The laws of probability suggest that in an infinite universe, unlikely events should occasionally happen, messages unscrambling themselves, shattered glass leaping back into place. Their absence hints that inflation's explanation, while compelling, might be incomplete. Could there be a deeper principle at work, something beyond our current physics that locks time into its irreversible march? The mystery takes a stranger turn when we consider black holes. These cosmic vacuum cleaners don't just swallow matter, they seemingly destroy information, erasing the history of what falls in. This clashes with quantum mechanics, where information is never truly lost. Resolving this paradox might require rethinking how time and entropy operate at the universe's most extreme scales. Some theories suggest black holes are entropy factories, churning disorder so efficiently that they reinforce time's arrow on a cosmic scale. Others speculate that the singularity at their hearts might be gateways to regions where time flows differently, or not at all. What's clear is that time's arrow isn't just a feature of the universe, it's a clue to its origins. Inflation provides a tantalizing starting point, but the full story likely stretches further into realms where quantum gravity and thermodynamics intertwine in ways we've yet to grasp. Every melting ice cream cone, every fading star, every memory you form is part of a cosmic puzzle, one that began with a flicker of order in the chaos of the early universe and continues unfolding moment by moment toward an uncertain future. The question isn't just why time moves forward, but whether we're seeing the whole picture, or just the shadow of something far grander. The precision required for cosmic inflation to work is nothing short of breathtaking. For the theory to match our universe's observed flatness, uniformity, and structure, the initial conditions had to be calibrated with almost unimaginable exactness. Adjust the inflation rate by a hair too much, and the universe tears itself apart or collapses before stars can form. Tweak the energy of the field ever so slightly, and quantum fluctuations fail to seed galaxies. It's like balancing a pencil on its tip for billions of years. Only instead of a pencil, it's the entire cosmos, and the slightest wobble means reality as we know it never exists. This razor-thin margin has sparked one of the most heated debates in modern cosmology. Is such fine-tuning a clue or just a cosmic coincidence? Some scientists argue it points to a multiverse, a vast ensemble of universes, each with different physical constants, where ours is simply the rare bubble where conditions aligned perfectly for complexity to emerge. Think of it like a cosmic lottery. With enough tickets, even the most improbable outcome becomes inevitable. In this view, the apparent fine-tuning isn't evidence of design, but survivorship bias. We're here to ponder it because only a universe this precise could host life at all. Yet the multiverse explanation leaves many uneasy. If other universes are forever beyond observation, does invoking them cross from science into speculation? Critics contend that without testable predictions, the multiverse risks becoming a metaphysical catch-all, a way to explain anything by positing an infinity of unseen realities. It's the scientific equivalent of saying anything's possible, which raises the question: at what point does a theory stop being falsifiable and start resembling philosophy? On the flip side, some see fine-tuning as a hint of something deeper, a yet undiscovered law or symmetry that locks the universe's parameters into place. After all, physics has a history of turning apparent coincidences into inevitabilities. Take the electric charges of protons and electrons. Their perfect balance once seemed arbitrary until quantum theory revealed the underlying principles that demanded it. Could inflation's precision similarly stem from a hidden framework we've yet to uncover? Then there's the elephant in the room, the designer hypothesis. While often dismissed as unscientific, it persists because it speaks to an intuitive unease with chance as the sole architect of cosmic order. But here's the rub: invoking a designer doesn't solve the problem so much as relocate it. Who designed the designer? And why assume simplicity when positing an unexplained intelligence behind the curtain? Science, at its core, seeks natural explanations precisely because they're the only ones that can be tested, refined, and potentially disproven. The real challenge lies in navigating the line between humility and hubris. Fine-tuning might reflect our incomplete understanding, not a fundamental mystery. Before quantum mechanics, the stability of atoms seemed inexplicably fine-tuned too. Today, we know better. Perhaps future breakthroughs will reveal why inflation's parameters couldn't have been otherwise, not because of a multiverse or a designer, but because the math leaves no other choice. Until then, the debate remains a mirror held up to science itself, reflecting both its power and its limits in the face of a universe that seems, against all odds, tailor-made for questions like these. Even among its greatest triumphs, cosmic inflation has faced fierce pushback from some of science's most respected voices. Nobel laureate Roger, known for his groundbreaking work on black holes and singularities, has called inflation not a scientific theory at all, a startling critique from someone who helped shape modern cosmology. His argument cuts to the core. If a theory can explain any possible observation by adjusting its parameters, does it actually explain anything? Imagine a locksmith who claims every key opens every lock. It might sound impressive until you realize it renders the whole concept meaningless. Contends inflation falls into this trap, morphing to fit contradictory data rather than making definitive predictions. This skepticism isn't just philosophical nitpicking. Inflation's flexibility stems from its dependence on the field, a hypothetical entity that can be tuned to produce wildly different outcomes. Want a universe that's perfectly smooth? Adjust the field's energy. Need slight density variations to seed galaxies? Tweak its quantum fluctuations. Critics argue this makes inflation, violating a bedrock principle of science articulated by Popper. A theory must be capable of being proven wrong to have meaning. If no observation could ever contradict inflation, is it really science, or just an elaborate just-so story? Yet inflation's defenders counter that flexibility isn't the same as vacuity. They point to precise predictions the theory got undeniably right, like the spectrum of temperature fluctuations in the cosmic microwave background. These patterns, meticulously mapped by satellites match inflation's quantum fluctuation origin story with uncanny accuracy. It's as if someone described the shape of a hidden puzzle piece years before the puzzle was assembled, and when finally revealed, the fit was perfect. For supporters, this predictive success outweighs concerns about adjustable parameters, especially since most physical theories, from the standard model to dark energy, contain some degree of fine-tuning. The debate intensifies when we consider testability, and others demand a smoking gun signature, like primordial gravitational waves with a specific polarization pattern, that would confirm inflation beyond doubt. The failure to detect these waves definitively, despite high-profile efforts like Bicep, fuels skepticism. But inflation's proponents argue absence of evidence isn't evidence of absence. They compare the search to hunting for fossils. Just because we haven't found a particular species doesn't mean it never existed. We might just need better tools or more time. Future telescopes, like the observatory, could still uncover the critical proof. What's often overlooked is how these critiques have shaped inflation's evolution. Faced with accusations of, theorists have worked to identify no-go predictions, specific outcomes that would definitively rule out inflation. For instance, certain patterns in the large-scale distribution of galaxies or anomalies in the cosmic microwave background would violate inflation's core mechanisms. It's a scientific tightrope walk, refining the theory enough to make testable claims without gutting its explanatory power. The tension reveals a deeper divide in how we judge scientific theories. Must every component be directly observable, or can we accept well-motivated constructs like the, if their consequences are measurable? History offers mixed lessons. No one has ever seen a quark, yet the standard model's predictions are so precise we accept their existence. On the flip side, the once popular theory collapsed when experiments failed to detect it. Inflation sits in this gray zone, not yet proven like quarks, but not disproven like the. Perhaps the most balanced view comes from physicist, an inflation pioneer turned critic. He acknowledges the theory's brilliance in solving major puzzles, but warns against treating it as dogma. Science progresses not by clinging to ideas indefinitely, he argues, but by relentlessly probing their weaknesses. Whether inflation survives these challenges or gives way to something stranger, the critiques have already done their job, keeping cosmology honest in its quest to unravel the universe's first moments. After all, the best theories aren't those that face no opposition, but those that emerge stronger from it. The quest to prove or disprove cosmic inflation is entering its most thrilling chapter yet, with a new generation of experiments poised to either solidify the theory's dominance or send physicists back to the drawing board. Imagine trying to photograph a snowflake from miles away, only instead of a snowflake, it's the faintest whisper of gravitational waves from the universe's first trillionth of a second. That's the staggering challenge facing projects like the observatory in Chile's desert, where arrays of telescopes will scan the cosmic microwave background with unprecedented resolution. These instruments aren't just upgrades, they're technological leaps capable of distinguishing inflationary signals from interstellar dust with 10 times the precision of previous efforts. If primordial gravitational waves are out there, their telltale swirling patterns in the polarization of ancient light could finally be captured, giving inflation the smoking gun it's lacked for decades. But gravitational waves aren't the only game in town. The European Space Agency's upcoming LightBird satellite will map the entire sky in microwave frequencies, hunting for subtle statistical anomalies that could betray inflation's handiwork. Some theories predict these patterns should resemble cosmic fingerprints, specific asymmetries or unexpected correlations that alternative models can't reproduce. Meanwhile, ground-based experiments like CMB-S4 plan to deploy 500,000 detectors across multiple continents, creating the most detailed portrait yet of the universe's infant years. The data could reveal whether inflation's quantum fluctuations truly seeded all structure, or if something even stranger was at play. The stakes get even higher when we peer beyond the cosmic microwave background. Next-generation gravitational wave detectors, like the proposed Big Bang Observer, aim to listen for frequencies far lower than current technology can reach, ones that might carry echoes of inflation's final moments. Think of it like tuning a radio to a station buried under static. The signal might be faint, but if caught, it could reveal the exact energy scale at which inflation occurred. Other include searches for primordial black holes, which some models suggest could be inflation's frozen quantum fluctuations collapsed into dense knots of gravity. Their discovery would offer a completely independent line of evidence, like finding a second witness to corroborate a crime scene story. Yet for all these ambitious efforts, the most dramatic outcome might be finding nothing at all. If next-decade experiments rule out primordial gravitational waves or uncovering consistencies in the fluctuation spectrum, inflation could face a crisis rivaling the one that birthed it in the 1970s. Already, dissenting voices like those of and Anna are proposing radical alternatives, from bouncing cosmologies to emergent spacetime models that don't rely on inflation's exponential expansion. The next great cosmological theory might be hiding in these null results, waiting for someone bold enough to connect the dots differently. What makes this moment so electrifying isn't just the potential discoveries, it's how they could reshape our cosmic origin story. Imagine learning that inflation was just one episode in a cyclical universe, or that dark energy is the field's dying ember. Perhaps we'll find evidence of bubble universes colliding with ours, their shockwaves frozen in the sky. Or maybe the data will point toward a reality where space and time emerge from some deeper quantum structure, making inflation not the beginning, but a consequence. Whatever emerges, one thing's certain. The universe's first moments are still writing their own mystery, and we're just beginning to turn the page. If inflation truly shaped our universe, it forces us to confront a humbling possibility, that everything we know might be nothing more than a statistical fluke in an infinite cosmic lottery. Picture walking into a casino where the slot machines never stop spinning, each one representing a pocket of spacetime with slightly different physical constants. In this grand multiverse, most combinations would produce barren, lifeless voids, universes where atoms never form or where gravity crushes stars instantly. Ours, with its delicate balance allowing for galaxies, planets, and conscious minds, might be the equivalent of hitting $1 trillion jackpot on the first pull. The unsettling question isn't just whether we're lucky, but whether our very existence biases our perception of what's normal. This line of thinking, called the anthropic principle, suggests that we observe a finely tuned universe not because it was designed, but because we couldn't exist to observe it otherwise. It's like a fish marveling at how perfectly water suits its gills, unaware of the vast dry land beyond its pond. Inflation's potential to spawn endless universes gives this idea mathematical teeth. If every possible configuration of physical laws plays out somewhere, then of course we find ourselves in one of the rare bubbles where life is possible. The alternative, that our universe is the only one, perfectly tuned by chance, feels like finding a single perfectly sharpened pencil in a landfill. Yet this explanation leaves some scientists deeply uneasy. If the multiverse renders every imaginable outcome inevitable somewhere, does that drain meaning from our scientific pursuits? Why search for fundamental laws if they're just local bylaws in our cosmic neighborhood? Philosopher Popper once warned that theories risk halting scientific progress, and the multiverse dances dangerously close to that edge. After all, if we can't observe or interact with other universes, does positing their existence explain anything, or just relocate the mystery? On the flip side, inflation's implications might be even stranger than a multiverse. Some interpretations suggest that quantum fluctuations during inflation could have created observer-dependent realities, pockets where the act of observation itself shapes physical laws. This isn't just science fiction, it's an extension of quantum mechanics' notorious measurement problem, where particles exist in superpositions until observed. Apply this to cosmology and you get a spine-tingling possibility. That consciousness isn't just a product of the universe, but in some way a participant in its creation. It's as if the cosmos needed observers to crystallize its own existence, a twist that would make Even's head spin. The debate touches on something deeper than equations. It's about how we define reality itself. Is our universe a self-contained entity with fixed rules, or just one thread in an infinite tapestry of possibilities? Inflation doesn't just challenge our models of cosmic origins. It forces us to reckon with whether those models can ever be complete. Every time we peer deeper into the cosmic microwave background or refine our theories of quantum gravity, we're not just doing physics. We're grappling with the oldest questions humans have ever asked. Not just how the universe works, but why it works that way, and whether we're here to find answers or simply to marvel at the questions. From blockbuster films to best-selling novels, cosmic inflation has become a staple of science fiction, though rarely under its real name. When movies like Interstellar depict wormholes bending space-time, or Doctor Who casually references the universe expanding faster than light, they're borrowing from inflation's playbook, even if the science gets Hollywood's signature polish. Take Marvel's Ant-Man, where the quantum realm operates outside normal physics, a playful nod to how inflation might have stretched quantum fluctuations into cosmic structures. But here's the catch. Pop culture often treats these ideas as magic, glossing over the grueling math that makes them plausible. A character might hack the fabric of reality with a technobabble device, while real physicists spend decades calculating how quantum fields could warp spacetime. Documentaries, on the other hand, face the opposite challenge. Series like Cosmos or The Universe strive for accuracy, but condensing inflation into a 5-minute segment risks oversimplifying. Imagine trying to explain the nuances of a symphony by playing just 3 notes. Viewers might grasp that space expanded rapidly, but miss the deeper puzzle, why it happened, or how a theory born from equations predicts the universe's structure so precisely. Even well-intentioned analogies, like comparing inflation to a balloon inflating, can mislead. Balloons expand into space, while inflation creates space, a subtle distinction that changes everything. Then there's the multiverse craze. Shows like Rick and or Everything Everywhere All at Once run wild with the idea of infinite realities, blending legitimate science with pure fantasy. While inflation does suggest other universes might exist, pop culture often skips the caveats, like how these bubbles would forever be beyond our reach, or that their physics might be unrecognizable. The result, audiences either dismiss the concept as silly or assume scientists are just guessing. Few realize that the multiverse, while speculative, emerges from equations that also predict things we can observe, like the cosmic microwave background. But pop culture isn't just a culprit of distortion, it's also a catalyst for curiosity. When the Big Bang Theory name-drops inflation in a joke or Contact visualizes wormholes, they plant seeds of wonder. Often says bad science in movies is fine if it sparks someone to ask, could that really happen? The key lies in balance, enjoying the spectacle while remembering that the true story of physicists like Alan scribbling equations on a late-night blackboard or teams hunting gravitational waves in Antarctic ice is often stranger and more thrilling than fiction. After all, reality doesn't need embellishment when it's already got runaway universes, quantum foam, and the lingering echo of creation itself. Explaining cosmic inflation to students is like trying to describe a fireworks show to someone who's never seen light. You need the right metaphors to bridge the gap between the unimaginable and the understandable. One of the most common teaching tools is the rising bread dough analogy. Picture a loaf of bread baking in the oven, with raisins scattered throughout. As the dough expands, the raisins move apart, not because they're traveling through the dough, but because the dough itself is stretching. This mirrors how galaxies aren't speeding away from each other through space. Space itself is expanding between them. It's a vivid, tactile comparison. Students can practically smell the baking bread, but it has a critical flaw. Bread dough expands at a leisurely pace, while inflation suggests the universe ballooned from subatomic size to cosmic scales in less than a trillionth of a second. That's like the dough exploding to the size of the solar system before you can blink. Then there's the balloon analogy, where dots drawn on the surface represent galaxies. Blow up the balloon and the dots spread apart, illustrating how space stretches. This works beautifully for showing how expansion doesn't need a center. Every dot sees the others receding equally. But it falls apart when students ask what's inside the balloon or what it's expanding into. Inflation isn't about space growing into some void, it's the creation of space itself. Trying to explain that with a balloon is like using a paper airplane to teach aerodynamics. It captures a slice of the idea, but misses the turbulence beneath. Educators often turn to the rubber sheet analogy, where heavy objects warp a stretched sheet to simulate gravity. Add inflation, and suddenly the sheet is being pulled taut at breakneck speed. This helps visualize how space-time stretches, but it glosses over quantum effects. Inflation wasn't just a smooth pull, it was a chaotic quantum frenzy, where microscopic fluctuations got stretched to cosmic proportions. Imagine trying to explain static on a detuned radio by waving a blanket. It hints at the noise but skips the electromagnetism. The limitations of these analogies reveal a deeper truth. Inflation is so far removed from everyday experience that no single metaphor can fully capture it. That's where layered explanations come in. Start with the bread dough to introduce expansion, then peel back the layers, switch to the balloon for scale, then dive into quantum fluctuations with a dice-rolling analogy. Each comparison builds on the last, like scaffolding, until students glimpse the full structure. The key is acknowledging where the analogies break. When a student points out that bread doesn't create more flour as it rises, that's not a failure. It's to discuss how inflation isn't just stretching space, but generating it. Some teachers bypass analogies altogether, using thought experiments instead. Ask students to imagine zooming into a tiny patch of space until atoms are galaxies apart, then hit fast forward to watch it explode to cosmic sizes. It's abstract, but it avoids the baggage of flawed comparisons. Others lean on simulations, showing how quantum jitters in a virtual early universe evolve into galaxy clusters. These tools don't just teach inflation. They mimic how scientists think, trading perfect clarity for conceptual honesty. The real lesson here isn't just about cosmology, it's about how we learn. All of science is a dance between the familiar and the unfathomable, and sometimes the best way to grasp the universe's strangest ideas is to hold multiple incomplete models in mind at once. After all, if physicists can tolerate the ambiguity of quantum superpositions, maybe students can embrace the idea that no single analogy will ever fully capture inflation, and that's okay. The goal isn't to perfectly understand the universe's first moments, but to get close enough to wonder what comes next. One of the most persistent misunderstandings about cosmic inflation is the idea that the universe is expanding into something, like a balloon inflating in a room. This mental image feels intuitive, but it's fundamentally misleading. The reality is far stranger. Space itself is stretching, creating more space rather than pushing into some pre-existing void. Imagine drawing dots on a rubber sheet, then pulling the sheet taut. The dots move apart not because they're traveling across the sheet, but because the fabric between them is elongating. Now take that concept and scale it up to cosmic proportions. Every galaxy, every atom, every point in the universe is being carried along as the very fabric of reality stretches. There's no outside for the universe to expand into, no edge to push against. The expansion isn't happening in space, it is space. This nuance trips people up because our brains are wired to think in terms of objects moving through space, not space itself rewriting its own dimensions. When scientists say the universe doubled in size during inflation, they don't mean it ballooned outward like a soap bubble. They mean every measurable distance between points abruptly, as if the ruler you were using to measure those distances suddenly grew twice as long overnight. Light traveling through this stretching space would, not because anything is moving away, but because the waves themselves are being stretched like taffy. It's a radical departure from everyday intuition, where empty space feels static and unchanging. So why does this distinction matter? For starters, it reshapes how we think about the universe's origins. If space isn't expanding into anything, then the Big Bang wasn't an explosion in space. It was the explosive appearance of space. This flips the script on questions like, where did the Big Bang happen? The answer, everywhere. The entire observable universe was once crammed into a volume smaller than an atom, and every point we see today was right on top of every other point. There's no center, no outskirts, just space unfurling like an infinite tapestry. Communicating this effectively requires ditching flawed analogies. Balloons and rising bread dough can help visualize expansion, but they smuggle in the very misconception scientists are trying to avoid, the idea of an outside. A better approach might involve digital metaphors. Think of zooming in on a fractal image. No matter how far you zoom, the pattern continues with no edge or container. The universe behaves similarly, stretching recursively without reference to anything beyond it. Or consider a video game where the developers keep adding new terrain as the player explores, not by loading pre-existing land, but by generating it on the fly. The universe does the same, creating space as it goes. Yet even these analogies have limits. The true nature of cosmic inflation might be something we lack the language or the brain architecture to fully grasp. After all, we evolved to navigate a world of medium-sized objects moving at slow speeds, not a reality where space-time itself is dynamic and quantum fluctuations dictate the fate of galaxies. Perhaps the best way to bridge this gap isn't through perfect analogies, but by embracing the weirdness head-on. Sometimes the universe doesn't owe us intuitive explanations. It's our job to stretch our thinking to meet it. What makes cosmic inflation so compelling isn't just its audacity. It's the breathtaking economy of a single idea unraveling multiple cosmic puzzles at once. Think of it like a master key that opens every locked door in a mansion, each revealing a different mystery of the universe's infancy. Before inflation, cosmologists faced a scattered collection of problems. Why space is so flat, why the cosmos looks uniform across vast distances, why no magnetic monopoles have ever been found. These seemed unrelated, like pieces from different puzzles. Then inflation arrived, showing how one explosive expansion could smooth out curvature, stretch quantum fluctuations into galaxy seeds, and dilute exotic particles to near nothingness, all in a fraction of a second. It's the scientific equivalent of realizing that lightning, static electricity, and battery currents are all manifestations of electromagnetism, a unifying framework that transforms chaos into clarity. Consider how inflation handles the horizon problem, the enigma of why the universe's temperature is so uniform everywhere. Without inflation, distant regions of space would never have had time to exchange heat, leaving the cosmos patchy and uneven. But with inflation's hypercharged stretching, those regions were once cozy neighbors, easily reaching equilibrium before being flung apart. It's like taking 2 cups of coffee from the same pot and placing them on opposite sides of a stadium. They're the same temperature not because they magically communicated across that distance, but because they started together. This same mechanism also explains the universe's eerie flatness. Just as blowing up a balloon makes its surface appear flatter to a tiny ant crawling on it, inflation's exponential expansion ironed out any initial curvature, leaving space balanced on a knife's edge between expansion and collapse. Then there's the puzzle of structure formation. The cosmic web of galaxies and voids isn't random. It follows a precise statistical pattern that traces back to quantum fluctuations during inflation. These microscopic ripples, to cosmic scales, became the gravitational seeds for everything we see. What's astonishing is how perfectly inflation's predicted spectrum of fluctuations matches observations, like a composer writing a symphony in the dark and having it played flawlessly by an orchestra billions of years later. Even the theory's apparent weaknesses, like the fine-tuning required for the field's properties, might hint at deeper truths. Perhaps the isn't an arbitrary addition, but emerges naturally from a grander theory, just as thermodynamics emerged from atomic motion. For all its unanswered questions, inflation embodies a rare beauty in science, the kind of elegant simplicity that feels inevitable once you see it. It doesn't just solve problems, it reveals hidden connections, turning a list of cosmic coincidences into necessary consequences of a single profound event. That's why many physicists, despite the controversies, hold on to inflation not out of stubbornness, but because nothing else weaves so many threads into such a coherent tapestry. The universe may yet surprise us with twists in the story, but for now, inflation stands as a testament to the power of a single bold idea to illuminate the darkest corners of reality. Cosmic inflation doesn't just stretch the fabric of space-time, it stretches the limits of human comprehension. We're creatures evolved to navigate a world of medium-sized objects and slow speeds, yet here we are, trying to fathom a reality where space itself can expand faster than light, where quantum fluctuations birthed galaxies, and where the entirety of our observable universe was once smaller than a single atom. It's like an ant trying to understand the internet. Our brains simply aren't wired to grasp such scales intuitively. This raises a humbling question. Are some cosmic truths forever beyond our reach, or is every mystery just a future breakthrough waiting to happen? History offers a glimmer of hope. There was a time when the idea of invisible forces warping space, what we now call gravity, seemed ludicrous. Or consider quantum mechanics with its particles that exist in multiple states at once, a concept so bizarre even struggled with it. Yet today, we manipulate these phenomena daily, from GPS satellites correcting for relativistic time dilation to quantum computers solving problems classical machines can't. Each of these breakthroughs began as seeming impossibilities, until someone found the right mathematical language or experimental lens to bring them into focus. Inflation might be no different, a puzzle that feels insurmountable now, but could one day click into place with the right key. Yet there's a chilling counterpoint. Some theories suggest inflation's trigger might lie in the realm of quantum gravity, where the very concepts of before and after lose meaning. If the conditions that sparked inflation existed outside our space-time, how could we ever observe or replicate them? It's like a character in a video game trying to perceive the programmer's keyboard. The tools to comprehend it might simply not exist within our framework. Even our most advanced particle colliders can't reach the energies present during inflation's first moments. We're left peering through a keyhole, catching glimpses but never the full picture. This tension between knowable and unknowable defines modern cosmology. On one hand, inflation's predictions about the cosmic microwave background and galaxy distribution align with observations to an astonishing degree, proof that we're tapping into something real. On the other, its foundational elements, like the field, remain frustratingly theoretical. It's as if we've mapped the shadows on a cave wall perfectly, but still can't turn around to see what casts them. Theoreticians grapple with this daily, constructing elaborate models that might never be tested, walking the tightrope between creativity and empiricism. Perhaps the most profound lesson inflation teaches isn't about the universe, it's about us. Our quest to understand the cosmos is as much about learning the boundaries of our own minds as it is about decoding nature's laws. Every time we hit a wall, whether it's the measure problem in multiverse theory or the arrow of time's origins, we're forced to invent new ways of thinking. Maybe the answer isn't to despair at these limits, but to embrace them as catalysts for ingenuity. After all, the universe didn't promise to be comprehensible. Yet here we are, piecing together the story of existence one paradox at a time, proving that even if some truths lie beyond our grasp, the act of reaching for them is what makes us truly cosmic. Studying cosmic inflation is like staring into a hall of mirrors where every reflection reveals a deeper layer of mystery. For physicists who spend their careers wrestling with this theory, the emotional whiplash is constant. One moment you're exhilarated by the elegance of a solution, the next you're humbled by a paradox that defies intuition. Take Allen, who first proposed inflation in 1980. He described the thrill of realizing his calculations could solve multiple cosmic puzzles at once, followed by years of sleepless nights questioning whether the math was too good to be true. That duality captures the essence of working on inflation. It's equal parts triumph and vertigo, like scaling a mountain only to discover the summit is an illusion and the real climb begins beyond it. The awe comes in flashes, when a telescope captures data that perfectly matches inflation's predictions, or when a student grasps for the first time how quantum jitters became galaxies. Cosmologist, another inflation pioneer, once compared these moments to seeing the universe wink back at you. There's something profoundly moving about tracing the lineage of stars and planets back to microscopic fluctuations in the fabric of reality. But just as often, researchers hit walls. The field remains stubbornly theoretical, like a ghost in the equations, essential for the theory to work, yet impossible to pin down. One postdoc I spoke to described the frustration of staring at whiteboards covered in beautiful, untestable ideas. It's like having a conversation with someone on the other side of a soundproof window. You can see the lips moving, but the meaning slips away. What keeps scientists going is the raw wonder of confronting questions that stretch the limits of human thought. Astrophysicist Levin recalls lying awake after a day of inflation calculations, her mind spinning with the realization that the universe might be both infinite and expanding, which feels like a Zen koan dressed in math. That cognitive dissonance, between the precision of the equations and the strangeness of their implications, is part of the addiction. You don't just study inflation, you develop a relationship with it, oscillating between reverence and exasperation. The emotional toll is real. Graduate students sometimes joke about inflation fatigue, that point in their research when the theory's unresolved gaps start to feel like personal failures. One researcher described the sinking feeling of presenting years of work at a conference, only to have a senior physicist shrug and say, "But how would we ever know?" Yet even in those lows, there's a peculiar camaraderie. Cosmology conferences often turn into group therapy sessions, with scientists trading war stories about dead ends and near breakthroughs over bad coffee. The shared struggle becomes its own kind of fuel. Perhaps the most surprising emotion is the quiet joy found in not knowing. For all its frustrations, inflation preserves a sense of mystery that first drew many scientists to the field. As Cosmologist puts it, the mark of a great theory isn't that it answers every question, but that it leads to better ones. Standing at the edge of what inflation can explain, peering into the abyss of quantum gravity, multiverses, and the true nature of time, researchers often describe a childlike wonder cutting through the fatigue. After all, if the universe had handed us all its secrets at once, what fun would that be? The beauty lies in the chase, in those rare moments when the pieces almost click together, leaving you breathless with the sense that reality is far stranger and far more magnificent than you ever dreamed. Cosmic inflation is more than just a theory. It's a cosmic dare, challenging us to rethink everything we thought we knew about the universe's first moments. The very idea that space itself could stretch faster than light, smoothing out the cosmos like a pane of glass while planting the seeds for galaxies, sounds like something ripped from the pages of a science fiction novel. Yet here we are, with mountains of evidence suggesting this surreal process might actually be how our universe began. That's the magic of inflation. It takes the impossible and forces us to ask, why not? What's truly remarkable isn't just the theory's audacity, but how it reshapes our place in the grand scheme of things. If inflation is real, then every star, every planet, and every one of us owes our existence to quantum fluctuations. Tiny, random tremors in the fabric of reality that were stretched to cosmic proportions in less than a blink. It's humbling to think that the vast web of galaxies we see today might trace back to subatomic chaos, frozen into the universe during its most violent growth spurt. And yet, that's not even the wildest part. Inflation doesn't just explain our universe. It opens the door to a multiverse, where countless other realities might exist beyond our cosmic horizon, each with its own unique laws of physics. But let's be honest, inflation isn't a done deal. For all its brilliance, the theory still has gaps big enough to drive a galaxy through. We've never directly detected the field, the mysterious energy that supposedly powered this exponential expansion. The primordial gravitational waves inflation should have left behind remain elusive, hiding in the noise of cosmic static. And then there's the elephant in the room. If inflation can be tweaked to explain almost any observation, does it risk becoming untestable? These aren't just minor quibbles. They're challenges that keep physicists up at night, debating whether inflation is the final answer or just the best guess we have for now. Yet even if inflation someday falls to a better theory, its legacy is secure. It taught us to think bigger, literally. Before inflation, the Big Bang was a singular event, a one-and-done explosion. Inflation transformed it into a dynamic process, a cosmic metamorphosis that might still be happening elsewhere in a vast, bubbling multiverse. It showed us that the universe's history could be stranger than we ever imagined, filled with quantum quirks and hidden dimensions. Most importantly, it reminded us that science isn't about clinging to comfortable ideas. It's about chasing the truth, no matter how bizarre it seems. So where does that leave us? At the edge of understanding, peering into the unknown. The next decade of experiments, from ultrasensitive telescopes scanning the cosmic microwave background to gravitational wave detectors listening for whispers from the Big Bang, could either cement inflation's place in history or send us back to the drawing board. Either way, the journey is worth it. Because every time we push the boundaries of knowledge, we're not just solving puzzles, we're rewriting the story of existence itself. And that's the real wonder of cosmology. The universe isn't just out there waiting to be discovered. It's inviting us to imagine, to question, and to keep reaching for the stars, even if the answers defy logic at